topic on multi-scale modeling of materials with the Digimat. He received his undergraduate and postgraduate degree from BSM College of Engineering, Bangalore, under Visvesvaraya Technological University, Karnataka. He started his career in Kirloskar Electrical Company, Bangalore, as a design engineer. He played a vital role in his company as a design of alternatives to suit end customers' requirements. Further, he coordinated with departments such as quality assurance, vendor department, assembly, painting, dispatching, and with subcontractors. Later, he joined in Pentas Soft Technologies Limited, Bangalore, as a project leader, computer aided engineering. In this company, as a project leader, he developed course material for CAE and also established his own CAE service team. In this period of project leaders, he presented and discussed with the end customers, including Defense Research Organization for outsourced CAE projects and supervisory service team in existing the project. Further, he moved as a position of a technical president for support team, service and service team, and also addressed the technical support, training, and service requirements. He worked closely with the aerospace, automotive, defense, manufacturing, engineering service providers, and other engineering organizations in India and abroad to address their CIE requirements. Currently, he is working with Hexagon MSc Software Bangalore as a business development manager, Indo-Pacific region. He involved in many roles and responsibilities like business development of structural and acoustic simulation technologies, enabling customers in the deployment of simulation solutions. Working with aerospace companies on structures, engines, and other subsystems simulations. Interacting with other machineries and equipment manufacturers on improving their design. Interaction with universities on usage of simulation for teaching and research. We are fortunate to have you as our chief for speaker for this FDP program, sir. I request you take over this session hereafter. Once again, I will welcome you, sir. Thank you.
Okay, thank you. Good morning, all, and welcome to this interaction on materials modeling using some of the simulation tools. I will be speaking for about maybe 40 minutes, 45 minutes on introducing some of these concepts. And then one of my colleague, Dr. Harish, will be joining in, and he will be doing a demonstration between for any question. You also feel free to and also type in any question. I will try to keep monitoring that. I'll share my screen just a minute. Can one of you confirm? Are you able to see my? Can you please confirm? Is my screen visible?
Yes, sir. Yes, sir.
Okay, thank you. Okay. So this product name, whatever I will be talking, is called as Digimat, and there's a lot of information available in this on this even in the public domain. I will be showing our company website also. But from your perspective, look at it as a generic concept. It could be Digimat, it could be any other product name also. The concept of the material modeling, what we are doing here, I will be trying and showcasing that. This is a brief background of our company. Our company name is called Hexagon, and within Hexagon company, there are several kinds of design and simulation technologies. Today, we will be seeing one particular you can say technology related to material modeling. It's called as Digimat. Earlier, our company was more popularly known as MSc Software. Now MSc Software is part of Hexagon group of companies. Now, when we say material modeling, we say that these could be the different aspects of material modeling. One term called ICME we use sometimes. We call it as integrated computational materials engineering, like that we use a term, which means it is not just like the material data. We may say, is stress strain curve only the material? We say something more is there when we say we have to work on materials in an industrial and commercial perspective. Different perspectives of materials engineering. One way to look at it, it is continuously evolving, and there will be newer perspectives also. So I will just briefly cover each of these, and then there are slides which go into details of each. First part is in a way the main focus of today's talk. It is virtual material development. What we mean by this is, you can see some kind of picture there where there is some curve, maybe something like a stress strain curve, and then there are some materials. We call it matrix materials, fiber material, short fiber, long fiber, and these kind of material we say. In general, we say generally composite material, like that we say. Okay, so when we say composite material, it could be like plastics, it could be like this injection molded materials, and then we talk of materials like CFRP, GFRP. There might also be metallic matrix composite, etc. So in general, composite means that there are multiple constituents inside that material, and depending on how we take those individual constituents, okay, what is the matrix material I will take, what is the type of fiber I will take, do I take a short fiber, do I take long fiber, how do I orient those fibers, are they randomly oriented, do I orient them in a particular direction, and then what is the process with which I will put together that material, maybe I will heat it for some time, and so on. So depending on all those, the individual ingredients and the process, I will get one resulting material, and that resulting material will have some you can say macro properties. Macro properties we are usually interested in: Young's modulus, Poisson's ratio, stress strain curve, and so on. These kind of parameters are what we will use in our design, in the stress analysis, finite element analysis, and so on. This technology, what it does is, or one of the thing what this technology does is, it will say that if you can tell the properties of the individual constituents and information on how those individual constituents are being put together, then this software will calculate and tell what will be the macro properties of the resulting material. Now, one of the advantage with that is we can design the material the way we want. That means for application, suppose we say, I want the ultimate stress to be this much, I want the yield stress to be this much, I want post yield stress to be this much, like that. For the requirement, it's possible to say that if I take this particular constituent, this fiber, this matrix, I put the oriented fiber like this, then I can get this material which will give me that required end properties. So earlier it used to be like, if I want to take some material for an application, maybe I should go on trying, I should test each material, see what is its characteristic, and then see whether that characteristic is sufficient for that end application. Now, sort of it is the other way. If I know what is the characteristic I want, I need not do iterations. I can go back and say, build the material like this. It will give us that particular required characteristics. And before we build the first prototype, we can simulate that all on the computer. Okay, that is what we mean by virtual material development. Some more details, examples, I will be showing that in the slides on that. Then we have got the concept of virtual material testing. Now, virtual material testing, for example, in aerospace, there is a concept called as coupon testing. Okay, coupon testing means whatever is the type of layup or material that they will use on every component, one set of samples they should take and test it. For every configuration that they want to try, they should test it. And only after testing, they will, that means they could change the layers, they could change the orientation, they could change the thickness, like that, of those composite material. Typically, we call them as the woven fiber composite, where there are multiple layers of materials, typically of There could be orthotropic, 2D orthotropic material. There could be some other like other material, multiple layers in between, and then we get the resulting properties. In any aerospace company, all that is available in the software basically. So this will help the aerospace companies to reduce the amount of coupon testing. They need not test for all the required configuration. Most of it they can do by the software. Then few critical configurations they can test it on the actual machines. This helps a lot in saving time and cost in the material testing for the aerospace programs. This also few slides are there. These are all available ready-made. I will show in the demo also. We'll be showing that shortly. Then the third aspect is called as the materials lifecycle management. What we mean by this is, if you take a large company, a large automotive company, they may have so many hundreds and thousands of materials that they will be using in various components. In the BAW, some material, in the tire, some material will go, in the engine, some material will go, in the rubber bushing, some material will go. Now, all that has to be stored in a very systematic manner, that, you know, so ideally some kind of online portal where somebody will log in and say, which product do you want to design? Which is the material options available? Which material do I use? And then it will tell, okay, use this particular stress strain curve. And then there is more to that. Where did that property come from? Because somebody will say, I took from here and did the analysis. Then the product might fail and it will turn out that maybe that data did not match the actual component being used. So it is very important to record, where is this data coming from? Did the company get it tested? Was there an in-house test done? If the test was done, what was the specimen used? What standard was followed for the testing? How many specimens were tested? Is there a statistical average? Or if we have taken from data handbook, which data handbook is it referred? Is that properly subscribed, and which volume is it available for reference? Which recent version of the data handbook? Maybe the data handbook people itself updated the data in one latest version. So all this information related to where is the data coming from, who brought it in, who tested it, which handbook is it coming from, is all readily available as reference in a transparent manner, by which we are ensuring that we take the proper material value. It cannot be left to chance what data to take for which application. And when we say life cycle management, we also mean like, okay, after usage of the product, maybe you will use the product for 5 years, 10 years, then what happens to that material? How should that be disposed? Can you just, you know, put it in some landfill? Should we burn it? Is there any other problem involved in that? So all that related information of the metal property, its origin, then its life cycle, everything, this is available as some kind of online information within the companies. Okay, and sometimes the companies may have units across different cities, across different countries also. In India, for example, a lot of engineering companies are there, mechanical engineering companies who are doing design here, maybe manufacturing somewhere they will do in some, you know, Thailand or Vietnam they will do. Then another design office is there in US, like that. So all this data should be properly available across all the divisions. Then sometimes there is some kind of a restrictions, security restrictions are there. For example, there is one security rule called as ITAR. It's an international treaty where certain material data cannot be given to certain countries, like that. Okay. Now this manufacturing company may have one office in one such country, another office in another country where that material cannot be shared. So you can share everything, but not that material. Like that, then it becomes a compliance issue. Okay. And for example, in some countries, some materials are banned actually. Okay. Like for example, one of our customer manufactures air conditioners. They are based in Punjab. They use normally inside the air conditioner one layer of a thermocol material they are using for reducing the sound. But some company in US they are exporting to, apparently they told them that that material cannot be used in US. It is banned in US. Now they have done their entire design assuming that particular material will contain the noise in some manner of that air conditioner. Now suddenly that company says you cannot use that material. So in a short time now they should use some other material. Then it becomes immediately, what was the property of that material, thermocol which we are using, which actually was used in the design. Now do we have an alternate material? And ideally that system itself should tell the designer that if this product is going to US, then you cannot use this material. The system should ideally be like that, so that it is not that you give to somebody and then they say it is banned. At the design stage itself, all these informations are available. This is available as of today itself in all the global companies, OEMs, etc. This kind of a system to manage all the materials. Material will go on getting updated continuously. Okay, so we did one test last year. Maybe this year, let's say some, every batch or once in every 10 batches of the suppliers, they go on doing the testing. Maybe last few years, some data was there. Now, since last 1 or 2 years, the same plate thickness and same material is giving, but the property may have slightly changed. So they go on updating this so that the latest updated information is available to the designers or the stress analysis people or anybody like that. So that is called as a lifecycle management system. It is usually an online portal developed and deployed for a particular company. These kind of things are in use now. Then we have a concept of material exchange where some companies are developing and like selling the material. There are specialized companies who will develop the materials. That company's work is to develop materials. For example, there is a company called DuPont. There is a company. If you say, I want to do this material, they will do iterations and this is the material. Now, those kind of companies, the sharing of the data, also they are doing online nowadays, okay, in a secure manner. The security is related to the fact that if one company is paying, let's say something, Tata Motors has paid to develop one particular material, that material should be shared only with that OEM, that Tata Motors, like that. That is also happening in an online manner. So that we call it as a material exchange, where there is interaction between the material suppliers and the end user in a secure manner. These kind of things can be integrated into this material management system like that. For example, the same DuPont may be developing material for even competition products. So to Tata Motors also develop a material, maybe something else. To Maruti also they will develop a material. But that data, they should keep it separate. They should not mix up like that. So that kind of systems are available in the online sense. You can say these are IT related, but there is engineering, there is material science. Finally, what is being shared is actually the material information. So that is everything should be focused on that basically. Okay. Then compliance and sustainability, same thing I told. Which materials are allowed, which materials are not allowed. The moment it becomes compliance, it's a big thing. It means now you sell something, even but you cannot say by mistake, I did not know that the material was banned. I include some material and export it to some country. They will seize all the shipment and they will say it cannot be used. And maybe they'll put a case against this company also. Why you are shipping that company, which is it's a legal thing. Okay, so that compliance also can be. So at the design stage itself, if we can say which product, which geography, which materials can be used, that thing is also available in the online systems, which our company and other companies are developing for the end companies usages basically. Then effect of processing, like for example, if we take the case of let us say injection molding, we will take. Okay, so I will injection molding is very common. There are several other processes similar to that, but this is a typical component. Hundreds and thousands of components we will manufacture by injection molding. Several intricate shapes and designs will be there. Now, when we are doing that molding, the way that the material will flow inside the mold and then the way it will solidify, that has an influence on the end material properties that will develop. Now, normally we will say, okay, this material means, okay, use this average property throughout the entire component. Normally we will do that, but that is not really the case. Depending on how that that mold is, somewhere very thin it is there, somewhere it is not, some dead end is there, some corners are there. There the flow will not happen fully in the other regions, and that has an influence on the properties that are getting developed in that region. Okay, maybe if there are some fibers, the fibers will orient in some manner in some direction, it will orient in some other manner in some other direction. So this is like a you can say it is like a non-homogeneous and anisotropic. Non-homogeneous means somehow that mold flow itself is not happening everywhere in a smoothly. On top of it, it is anisotropic. If some fibers are there, depending on that flow, the fibers are getting oriented. This, how do we account for? What we do is like this. There are some simulation software which will simulate the injection molding process itself, basically. Okay, so there is a product called, for example, Mold Flow is one name of the product. There are several other products which will say, if this is the die and the whatever the mold, and this is the material that you are manufacturing by induction metal processing, how will that injection molding process? It will simulate that flow. How will it finally solidify? And finally, what will be the fiber orientation and density of the material in different directions? It will calculate. This is the process simulation. But once we have that process simulation, what this tool like our Digimat will do is, it will study that information, what is density, what is fiber direction, etc. Based on that, it will calculate the mechanical properties for different regions of that final molded component. It will say in some region it is a bit weak, so Young's modulus is less slow. It will basically estimate the stress strain curve for each part of the mold, you can say. Okay, and depending on the flow that has happened in the mold, some parts will be stronger, some parts will be weaker, like that we can estimate that for an actual molding that has happened from the simulation. And that one we can automatically transfer or map onto the finite element model. Now in the finite element model we have a mesh which is of some component like this. In finite elements, in principle, you can apply a different material property for every element also. You can do that because the stiffness matrix is at element level. We may not do it for every element, but for one set of elements, automatically, it will study that final molded configuration. It will estimate the properties for each part of that component, and it will automatically map those properties onto the corresponding finite element mesh. Okay. Then we just set up our loads and boundary condition, we run it. This simulation will be much more realistic as compared to assuming a common material property throughout the component. This can make a significant difference in the end product behavior. Okay, because end product is going to behave like the actual real component only. It is our assumption that we were simplifying that, and I will show you some case studies also where this can be done. So this means that is what we mean by effect of the process, means the manufacturing process or the component creation process on the end material properties. We can estimate that. On top of it, there is these things also, because of the fiber, the orientation, some properties there. Because of this flow, some change happened. All that together will get accounted and calculated and mapped automatically onto the finite element mesh. Okay, so this kind of thing is also available. And same thing related to accurate material modeling. It just means that overall in our model, it is much more accurate, the representation of materials like that, instead of assuming some things. And then, for example, we have now additive manufacturing is a big thing now. A lot of components, earlier it was more like maybe some special prototypes or special materials, we will use some 3D printing. Now, anything and everything, do 3D printing, even like in a production method, do the 3D printing. And the concept is like now, even inside the production shop, you set up one additive machine, AM machine, and print the parts and it goes to assembly. It has come to like that now, basically. Now, when doing that, what materials do we use for the 3D printing itself? We can do iterations. Okay, there are multiple options depending on the end usage. If I use which material, which is better amenable for a particular 3D printing process, like that we can estimate in a material design, and then we can automatically apply. Now there is also that 3D printing process itself can be simulated. Just like I said earlier that the injection molding can be simulated, the 3D printing can also be simulated. Now for that 3D printing simulation, that input material properties of that material we can calculate with the software, this Digimat software, for various different kinds of alternatives, and input this data into that 3D printing simulation. Then from the 3D printing simulation, they'll first simulate the process parameters. That means what should be the orientation of the component, what should be the support structures, like that, etc. You can do various iterations, because it is not like you simply take a component, print it and use it. It doesn't work like that. First few components will all go, several distortion will happen, several breakages will happen, like that. There is quite a few parameters involved in that. So all those process parameters, especially support structure and how do we orient the component for printing, is a major thing to be done. Now all that can be simulated first in the computer, and then the correct or finalized configuration can be printed, so that there is no wastage of the materials, etc. In India, now it has gone into a production mode wherein there are what we call as the 3D printing bureau companies, we say. That means that is a company dedicated for 3D printing only. Just like we go and say, you take some paper and print a paper report and come, these companies will be there. You take your CAD model there and specify which material, they will print and give you a part, you can get back your part, like that. And their company's business is for doing this one only. All those companies are now first doing the simulation. If somebody says, print me this part, first they will open the computer and say, okay, this is the part. How do I set it up for my machine? What support structure? What orientation? Which material should I use? All these things, they simulate that. Then when they verify everything is okay, then they will proceed with one sample part testing, like that. So for that whole process, which material options we can use, we can arrive at from this materials engineering processes or material simulation. And then we are talking of, for everything, anything and everything we are telling nowadays, artificial intelligence, machine learning, like that we are telling. Same thing can be used in the materials engineering also, meaning that if we want to try out some large of the right? Traditionally, it is like I have to create one finite element model. We can script it, but still it is creating one finite element model. It is doing one nonlinear analysis. It is detecting what is the stress level and it is reporting it. This is happening continuously in the batch mode. Okay, maybe each run will take maybe some 15 minutes. It will take like that. So you want to do 1,000 runs, 15 into 1,000. So many minutes time is needed for that. Now with this AI and ML, what the concept is that we give it some initial data or some training data. That means some 10 different or 20 different coupon configurations, extreme configuration. I will test and I will give the stress strain data to this artificial intelligence software and say that if configuration like this, curve is like this. If configuration like this, curve is like this. Then I can ask it, now in between these configurations, you take this 1,000 other configuration and you give me the output like that. So it will somehow build a mathematical model on this training data that you are giving it. So usually once we ask it to train the model and we will ask it to do some testing, we will do. That means we will say, okay, predict one behavior, we will say, it will give one curve. That we will actually do the full simulation once and see whether, okay, is that matching with that or not. If it is matching, that training data is well sufficient. If it is not matching, it means some more use cases data you should give. The data can come from testing, the data can come from simulation. So like this, we do a verification first. Once we are able to match to the sample case, then we can say, now you do that hundreds and thousands of combinations. Now, once the mathematical model is built, any further hundreds and thousands of iterations can happen in a matter of seconds actually, because it is working in a different manner on a data model like that. So that concept is used for materials engineering also. And we are also providing some similar solutions for that, some company also. So AIML, the key thing for it is what we call the training data or the input data. It will study that. Then there will be some mathematical models. It will create one mathematical model, and then using that, it will predict the data like that. Engineering is very much there because we should be clear what are we inputting, and that test cases, whatever it is predicting, is it okay? That we should continuously monitor. And then if it is okay, there are so many methods, so many algorithms to do that. Which one will best suit our case? That is where we have to check that carefully and monitor the output. Is it coming properly before we start using those material models? And so on. And we also call it as digital continuity, digital twin, like that we'll say, overall for the digital modeling. So these are all some aspects. And the title itself, what I put it as multiscale material modeling, or MSM, what we say. Multiscale simply means that we are studying the behavior at the micro level, this fiber, matrix, orientation, distribution, etc. That is micro level. We are seeing what input go, and knowing the micro level, can I predict the macro level, which is the input into the finite elements, like, or any other end usage, like Young's modulus or whatever it is, shore hardness, stress strain curve, ultimate stress, like that. So we are connecting both modeling at micro level, getting the output at the macro level, or for a given macro level property, what should be the micro level, we are studying that and designing that. That is broadly what we mean by the multi-scale modeling in that sense. Do you have any questions so far? More or less now on the same things, I will be showing several use cases, examples, projects, etc. I will be showing on the things. Anybody has any questions, you can ask.
Yes, sir. Sorry, is it the free version or the paid version?
That's a good question. We are providing both actually. So if you see our website, this is our website. You can just type mscsoftware.com. Okay, you will see our website here. In this, there are a lot number of products involved. Can you able to see my screen? Can one of you confirm first?
Oh, it's showing off.
Are you able to see my screen? Can one of you confirm?
No, sir, it's showing off.
1 minute. Okay. Let me check that sharing once again. Sorry. Where is that? That is here. Okay. Yeah. Now are you able to see?
Yes, sir, we can able to see now.
Okay. So this is our website, mscsoftware.com. Okay. Easy to remember and type. So here, more or less information on all products are there. If you go into products, okay, and you see into this, you can say integrated solution, we call it, because whatever, there is the pre-processing, post-processing, everything is there. Under integrated solution, you will see this Digimat. Okay, this I hide. So you will see products, integrated solutions, Digimat. Okay, so if you click on this, this web page will come here. Okay, so multi-scale modeling. So whatever I'm telling, all that is given in much more level of detail here actually. Okay, you can see here, investigate and predict behavior of large mix of composite material, design and manufacture high performance composite parts. What we mean by high performance is at high temperature it should have good strength, like that, complex behavior, minimize the weight, cost, like this. So these are all things are there. And now there are so many details what we'll do, different modules, all that information is here. Okay, that is one part. Then you will also find this case. I'll be showing some of them under case studies here. You will find plenty of the case studies. Some of them I will be showing that also. This is the information on general, this Digimat. Now coming to what you ask about the colleges access to that, here in our main website itself, under academia, you will see one tab called as the student editions. Now for the students and for the colleges, we are offering a free software, which is a sort of a limited version. It is not having all the 100% capabilities as that of what the end companies are using. So you can see these are all products of the student version we are offering, and that includes the Digimat also. However, from the college perspective, although we say compared to commercial perspective, it is limited capability, but the students anyway cannot learn all that any commercial company can do. We need several years to learn that. From a college perspective, whatever we are offering for student version is much more than enough. If they can understand that much and do, it is more than enough. Any industry will be happy to take those people if they have learned that much itself also. So here under this, so once again as a summary from the main site, academia, student edition, here you will find all these, this ones, sorry. Student edition, you will get all these things. Go to this Digimat. If you click on this download now, it will ask the students to, this is free. This is free ideally for a student. Okay, so even if the staff want to use, you can ask one of your student to register, and once he will download, just ask him to share that installer with you. You can use it. So it will just ask for the mail ID and so on. And important, it will ask for one student ID. We are just in the backend keeping track of which college, which student, and which year you are graduating, like that it will ask. Okay, we will invariably give access to 100%. In 1 or 2 days, they will get an email giving the link from where they can download. So our suggestion, you start with that. Okay, and you can approach us also through Dr. Raja Reddy. You can send me a mail. Me or one of my colleague will help you with that. First, to do whatever is available in that student version. If you need more than that, then we will provide you that software. Okay, then maybe eventually your college can look at buying also. But before you look at buying, there is a lot that you can do with the student edition free itself, basically. Okay, so in that sense, it is available free for students. Whatever I am telling, you can start with this. Is that okay? Is that clear?
Yeah, understood, sir. Understood, sir.
Okay, sure. And I would even encourage use all the software also. Okay, Digimat is only one software. Nastran is a very widely used structural simulation software for structural static analysis, dynamic analysis, so on. Then Adams is very widely used for the this motion solve for the mechanisms, and then for all the vehicle dynamics and so on. So any software is worth practicing. You can practice multiple also, but at least one software you can practice is good. In this today's talk context, it is centered on Digimat. In fact, if you register, you actually get access to all the software actually. Okay, with the same registration we provide to all the student versions. Okay, so that is the sum. So I strongly recommend to people register that, download that, do some tutorials which are present in that, take up some small project as part of that. Even though it is small, if you understand and do well, industry will value a lot that one. So, but you have to do genuinely. That is the thing, not simply copying something somebody has done. So even very small and simple you do on your own, there is lot of weightage. You tell that in the job interviews, you will get the jobs if you have done properly. These kind of things is my input on that basically. Okay, so let me come back to the main presentation. So any other questions from anybody?
Sir, is there any self-learning kind of videos or any PDFs are available?
Yes,
to
it
do
is.
some
Once
analysis?
you download the student version, inside that only all the tutorials will be there. Okay, that is one comment. And second thing is, in general, in YouTube, etc., you will find several videos. But the starting point can be you download the software. Inside that only all the tutorials are available.
Okay, fine. Thank you.
And in any case, you just download, try for some things, then send me a mail through Dr. Raja Reddy. We will help you further on that. Okay, but that first you have to download and first you have to do something on your own. At least even if you get stuck up, do something and then reach out to us. We will help you. Okay.
Sure, definitely, sir.
Okay. Any other questions from anybody? Okay, I will continue further. So now the next is basically a elaboration on all these things for about maybe another 5-10 minutes. Then by the time my colleague Dr. Harish will be joining, and he will be demonstrating this actual product. Let me check once in case he has not. Okay, no problem. I will alert as soon as he joins on that. So now we will just see few slides which are basically details of whatever I have been telling under specific references like that. Now this is one of the view of the software. I would say this is a slightly couple of years older software only. We have improved it further, but this is some of the thing. When you open the software, it looks like this. These are all the different modules. Modules means different capabilities. We can see here, this is some stress strain curve it is predicting. This is, some fiber we can make out something like this here. Then this is like a map. Map means from that injection molding material configuration to the material calculation to the CAE like that. Okay, that is what we mean by that mapping. Then, for example, here we have these, this hexacore kind of materials are there. This is something specific to that. If you specify the properties of the core, it will calculate the resultant properties, which is very widely used in composites. Okay, then this is that virtual testing, okay, coupon testing that is there. This is the additive manufacturing and so on. Okay, there are some users manual, all these things will come as part of that. And this is just to show that the companies are using it. It is not that simply these are concepts. Even as of today, all this data is again few years older. Okay, today it is much more also. So all the auto suppliers, all the aircraft suppliers, aircraft engine people are using this kind of technologies. Okay, here some names are there. Now these are some of those material manufacturing companies. I mentioned DuPont. Like DuPont, these are the other companies, Solvay, Sabic. Okay, a lot of these companies are present in India also. They are basically creating the materials or designing the materials for the end users. Okay, so they are the material specialists, you can say. They are using products like this to simulate and get the correct behavior. And here we are giving some view. If we say a car, so many parts of the car is having this, composite materials, and there is scope to use this kind of technology to design the correct material properties for all of these applications. It is being used on a day-to-day basis like that. Similarly, if we say aircraft, so many parts of the aircraft are on composites, and these technologies are used to predict the properties for a lot of these components and subsystems. Okay, again some general view of the same thing. Some material CFRP, SFRP, DFC, sheet metal composite we say. SMC is another interesting type of metal which is widely used. Metals also we can do. Then foams, rubber, and so on. All these materials can be worked on or designed. And so we start from the material and then use that metal property with specimens first to verify how it is working. Then finally we will apply it on the fully end component. We will apply like that. And again, these are just general slides. I will skip further. This is the same thing, whatever I showed earlier, more zoomed in view. This whole presentation I will be sharing with you as a PDF. Today evening I'll share, and then Dr. Raja Reddy can get it sent to you. And so this is one of that example, what we are telling. If you take a component like this, okay, for example, depending on that molding condition, in different regions, there could be different fiber orientations that will come up with. So there might be so many different stress strain curves. In each region, it is behaving in a different manner. Okay, this is what the Digimat software will have. This Autodesk stands for the mold flow. Okay, the product is called mold flow, which will simulate the molding. Now, depending on that, you will find here maybe the fibers are like this. Here it is like this. Here it has ended up like this. That is because the mold flow is happening. This is where that whatever riser and runner, those things are there. Okay, that we will capture first. Then for the resulting fiber orientation, each one is of that. So you can see we have colored coded here. It says in this region, if the fiber is like this, the stress strain curve is like this. Okay, in this region, if the fiber like this, stress strain curve is like this. In this region, if the fiber is like this, stress strain curve is like this. Okay. Otherwise, normally what we do is we assume some average behavior and do everywhere, but the material is actually behaving differently. So somewhere if you say this is some yield or this is some ultimate, you can see a lot of variation is there. This we are accounting for in this multi-scale modeling, material modeling process. Okay, so same thing, the manufacturing process, then we import the manufacturing process detail. Then with a tool like Digimat, we are calculating the different stress strain curves, and then we are calculating the final performance using the appropriate data. Okay, again, some more details. So I said process, no, it is not just injection molding. So many processes are there. Okay, these are some of the softwares used. For example, this, there are metal forming could be there. We have this, like, Uniform is there, then Magma. So many tools are simulating so many processes. Okay, for example, we even have some scanning processes. That means you can say, I take some component, I will do some scan of that. That means, and then scan like our, what we do, our this one, no, like our X-ray, what we do. Now imagine you take an X-ray of entire multiple sections of that component. From that multiple, this is industrial scan. Industrial scanner means it's much more accurate. Okay, so it will take those multiple cross sections and it will put together and create a 3D geometry actually, and 3D material, 3D representation of what is inside also it can capture that actually. Okay, like whatever void is there, whatever orientation is there, it will capture that. That kind of data, again, a tool like Digimat can read that and it will calculate the property now based on that specific type of, imperfections it is there, or whatever fiber is there. That kind of thing is also available. So practically a wide range of simulation, we can read in the data, account for the correct variation of material properties. It is no longer just one Young's modulus, one Poisson's ratio. It is now varying from position to position depending on whatever has been the process that thing has undergone. We calculate all that, then that we map onto practically any software. Now this technology as such is independent of software. We can use whichever process simulation software we have. We can use whichever simulation software you have. These are most of the all available solutions in industry. This tool like Digimat will map the process from any process simulation to any finite element analysis software, and we can do the further analysis. This kind of technology is being used. It is available and being used in the industry. Again, same thing, we will elaborate on that. So like, you could have the matrix, you could have the filler material, and then the orientation, and then we have things like volume fraction and so on. So with the different combinations of this, it's called as homogenization methods are there, different equations are available. Then it will predict that if the fiber orientation is like this is the property. If the fiber orientation is like this is the property. So depending on the fiber orientation, you will get some appropriate property. We can visualize this and so on. So all these kinds of, and this will get mapped onto the structure. Calibration we can do. Whatever we will predict, what is the guarantee that it is working correctly? We say one specimen you simulate with all this technology, whatever simulation we are doing. Then you simply take one actual specimen by that same process and do the testing. Then compare those two. Like that, plenty of comparisons we have done, which is verification that this whole method is working like that. Okay. And so these are the kind of software. If you open the software, you will see that. So you can see so many materials are there. Okay. Lot of used, industrial wide variety and configurations of materials. We have the data for all this. I mean, these are the individual constituents. Okay. This is when we say chopped fiber. Okay. Short chopped fiber. So many types of fibers we are having the property practically. So we have tied up with practically all of the material manufacturers. So we know that if they say chopped fiber, they will be using one of this only. Okay. So it will take the property from here. All we need to know is what is the volume fraction, what is the orientation, like that. Then it will put together and it will calculate the global property like that. Okay. So the experimental curve of each of these individual constituents is available inside the software. Okay. For the end usage by the user. Okay. So that is being done by all these companies. So those individual constituents, whatever these are there, are actually developed by all these companies. So we are working with all these companies to create that database of thermoplastic, thermosets. So you can see there are some 342 grades of some 28,000 materials we are offering. You can combine them and get any required property or characteristic the way you want. And these companies themselves are using this software so that they know how it works and what comes at the end of it. So again, just to mention, so many types of things are there. It is available. So for all these kinds of material and something more also, knowing the micro property and accounting for residual stress, weld line, fiber length, porosity, accounting for all this, we can predict the end macro property which that component will have and use that property in the final simulation or design, so that our simulation is correct and more realistic, basically. Okay. Mapping solution. Mapping means from that molding onto the this thing mesh, because the thing is that mold flow simulation or injection molding simulation wants the mesh in some manner. Our finite element stress analysis has got mesh in some other manner. So we should be able to map, Okay, sometimes something is in 2D, sometimes is in 3D, like that. So that 2D to 3D, something, whatever. The region of space will be same, but the meshes will be different. Maybe it is 2D and 3D, it is there. Sometimes units may be different. But in spite of all this, we should properly transfer the material information from the one mesh to the other mesh. Okay, that is called as the mapping solution, which we are able to do. Just give me a minute. Okay, sorry, continue. So this is again same view of multi-scale modeling, whatever we are doing. So each of these places, there is different orientation, different stress strain curves. And so structural simulation, virtual material testing, effect of the defects and manufacturing process, additive manufacturing, these kind of things. And now some industries where they have actually used, okay, day to day in India and globally, we are showcasing that. So Faurecia company, they manufacture several kinds of components. In India, they have multiple, you can say, design centers, engineering centers. They work with Solvay. So usually there is a end component or end system designer, and then there is the material supplier. They always work together within this technology. So they work with Solvay, and they have used for several applications. Some of them you can see here, injection molded composites. Finally, what is the aim is 30 to 50% weightage saving. And our simulation is much more realistic. So we thought it will behave something like that. Now it is behaving like something else. We are able to do the accurate prediction. Okay, this is one of the main aspect of it. So for example, Faurecia seating systems is there. That is one of their units. So whatever you can say, the metal to plastic replacement, we say. When we say plastic, we mean composite material. Okay, so this particular component, just give me a minute. Just give me 1 minute. One call is coming. I'll just check what is that.
Problem?
Yeah, sorry, I'm back. Sorry. So,
Okay, sure.
so we continue. So these are like the metal to okay, these are now 1.66 kg, and metal also is being avoided to be used like that. Okay, and they are simplifying the design also. When they do the injection molded part, it's like you can combine multiple parts to get one integrated part. Okay, so the assembly also becomes simpler, like a 50% part reduction. All these are sort of done together. And now the main thing is which material you can use for this, so that it will have the same strength as that of the original part, like that. Okay, so that is the part what is being done here. Okay, so several views of that. When we do the analysis, this is how the, you can say, the orientation of the fiber. So some places it is randomly oriented, some places it is having a strong directionality. This depends on that process parameter. We are simply reading from the process, and then we are calculating the correct material properties and using it in the design. Okay, and so here again several things. So for example, these kind of systems here, which are holding these seats and so on. You can see the part is shown here. And other things like same thing. So correlation with the test. Okay. Finally, they will do the test and say whatever, some load versus deflection or stress strain, they will match and say that, okay, it is matching well, which means this whole process is working okay, like that. Those kind of verifications are available. This is again multiple experiments they have done, and force versus deflection. So finally, these are kind of verifications. You do a test, you see the force versus deflection, and then we will do like that. And similarly, reinforced plastic. And this is, for example, this Value company has done that. Like in the case of this vehicle engine cooling radiator. Okay, so this part, they are making with a this composite material, and to ensure that it is working okay and that kind of things. So isotropic versus Digimat. So normally they will assume that it is an isotropic property. Okay, and they will do the design. Then it turned out that that was failing actually. Okay, because that part was not actually behaving like an isotropic property. Then they did all these simulation of the metal properties, got the updated properties, accounting for all these aspects which I am telling. Okay, and then with the newly designed material property or the updated material property, it is working properly, like that. Okay, so earlier they took the assumption of isotropic property and do the analysis, and okay, the design was not working. Updated property coming from this multiscale modeling, accounting for all the whatever the orientation, the distribution, etc. We get a different material property. With that component is now working, and it is not breaking like that. Okay, this is the company reference from Value. Value is again in Chennai. They have got large engineering centers, all mechanical engineering, you can say work only they are doing, and they are using technology like this that is being done. Okay, so they are comparing that. What was the isotropic means? It is assumed value, and then with this materials engineering, how are we getting the better behavior like that in that sense? Okay, then so several companies, I'll just quickly run through. This is from another company like Volvo. Okay, and there again in the this crash analysis, especially the bumper or some of these components. So you can see this component is present here. Okay, crash analysis is a very you can say extreme analysis where it should withstand the materials and ensure that the rest of the system is not damaged. So they have used these kind of materials. Isotropic means that was the assumed value. With Digimat means more realistic value which they have calculated and used it for the designs. Okay, and this Moldex is another tool which is used for the injection molding. I mentioned earlier mold flow, Moldex, like that. So many other tools are also available which can be used. This is another company, Socaris Engineering. They have used for this kind of applications. And this is again from okay, so that is a brief overview. Again, any questions on this so far? Again, last few slides I will summarize, and then my colleague will do the demonstration of this. Any questions as of now? Okay, I will continue. My colleague Harish has joined. I can see that. Another few minutes, I will just wind up, and then we will they will do the demo. So this is for the additive manufacturing, like I was telling. So why is additive manufacturing simulation important? Because there will be warpage, there will be internal stresses, there could be some gaps, there could be porosity. We have to account for all these things in the material behavior of. One is there is the additive manufacturing process parameters itself is there. Apart from that, the material also we should take it suitably so that all these challenges and defects are minimized. For that, we are able to design a better material. So this material will go into the 3D printing simulation, and then we verify that the process is happening properly. Okay, so we are working with all the other, the Stratasys, for example, is one 3D printing company. Then Bosch, DSM, all these companies are using 3D printing, and they are using these kind of technologies. Okay, so you can see here again, this Harish will cover further. FFF, SLS are different processes. So for example, we can do some topology optimization, although it is not directly material. In additive manufacturing, what is happening now is there is no constraint on the shape. Earlier means if you had to cast, if you had to extrusion, etc., the shapes have to be of some particular shapes. You cannot manufacture any arbitrary shapes earlier. But now with 3D printing, anything and everything you can print. Okay, of course there should be suitable support structure, etc., but practically anything can be printed. So optimization now we can go to any kind of arbitrary and even weird shapes, but it will still work and it can be printed like that. Okay, so topology optimization is a big thing. Then this fiber orientation, etc., process simulation, then the part performance, and then the part inspection also. We are offering the methodology for those kind of things. Okay, so again, reiteration of same things which we do. And so which are the types? For example, FDM, SLS, for all more and more processes, we are able to define the material characteristics and so on. Then, for example, visualize. These are all some more screenshots of the software. We can visualize these lattice structures. Then virtual testing, like the coupon testing we can do. And now these are the materials used in 3D printing. Okay, we are getting that data directly from the material suppliers. This is still in 2019. Now we have much more. But Solvay is company which develops the materials for 3D printing. That characteristics we are having in our software, so that you use that in the simulation and ensure that the design is correct. That means what is the property at the end of the 3D printing? If you use this material, we know that property. Okay, and we can calculate and you can simulate from that basically. Okay, again, for example, effects of warpage. Okay, and for example, warpage evolution. So here, for example, now there is something called as the compensatory offset. What we do, that means because of the 3D printing process, some warpage will happen. So we will make our initial shape in the slightly opposite direction to have a, you can say, a curvature, so that after the warpage that actually happens, you get the correct shape like that. Okay, that is called as the compensatory offset. What we do, those kind of things we can design and account for it. Okay, again, there are several examples of those kind of things. And again, part performance, we take a better metal property to ensure that it is not going to break like that basically. Effect of microstructure. Okay, which type of microstructure, how it is influencing the macro properties, like that we can visualize. So here is some failure investigations and failure simulations we have done. Again, some more examples, like some cooler application. Then again, some sinterline powder, the sintering processes and so on. The powder that is used for that, we can use it to simulate that particular behavior. These are again some screenshots of that similar warpage compensation. Okay, and again some tests basically, which we will do to check that, and so on. So that's the brief summary. Okay, basically to say that for practically any materials application, study the end properties you want. For that, we can design what is the kind of micro properties we need to ensure that we get the correct material. If there is any process happening, take the process effect also into account, and then update the correct material properties on the simulation model, so that the simulation is much more realistic. This is used in a wide range in the industry. Okay, that's the brief introduction. Again, any questions you can ask me now. If not, my colleague will start with a demonstration. So I will just stop sharing for now. Harish, can you start? I'll give a brief introduction and you can start maybe.
Yes, Vivek.
Yeah,
I will start it.
Yeah, so I'll just briefly introduce you. So once again, to all the people present, Dr. Harish works with us. He is specializing in this material engineering. He joined us a couple of years back. He has completed PhD from IIT Madras, and his area is in the work is in the area of mechanics and materials and so on. He is focusing, dedicatedly on this materials engineering. He works with all those companies and projects which I told. He has been part of those kind of things. He will give a demonstration of that actual software. How does it look like? What is the input? What is output? Harish, you can take about maybe half an hour to 45 minutes, and then in between keep asking some questions also. Let them ask questions, pause so that they will understand the things also. Okay.
Hi, my name is Harish. I'm working as a technical specialist at MSc Software Hexagon. To give a small introduction, I did bachelor's at civil engineering JNT. I think it is near to you, the Puttaparthi. So, like that. After that, I have did masters and pursued PhD. So now I will share my screen and give you the demonstration of the few tools may not be completely possible to demonstrate for all the tools. But I try to give you what is the insight and objective of the Digimat with my demo. So don't hesitate to stop me if you have some doubt or want to clarify some questions. So let me share my screen. So you can see my screen in a minute. Okay. I hope you are seeing my screen, which I have shared. So if you have a Digimat is actually meant for the composite materials for short fibers or any filled fibers, or let us say matrix with voids or matrix with continuous fibers, or additive manufacturing materials like tool path generated composites and filled composites or unfilled composites, etc. So at this moment, what industry is facing is the accuracy, as actually the Vivek sir explained. So there are some case studies explained, and those case studies are carried out in tier one companies and OEM companies. What they are actually facing the challenges is when they are actually working with the composite materials and doing the simulations, they're not able to predict the right behavior, and when they're comparing with experiments or the validating with some other source, they're not able to see the failure locations in proper way as they see in the experiments, or they are not able to correlate the stiffness which they are actually getting in the realistic world, etc. Those things are actually to correlate and to do the uh, predict the right performances. We are actually at this moment, the industries are actually coupling their infinite element simulations with the Digimat to rightly predict the performances. So that is the main objective why the Digimat comes into the picture when they are doing the simulations. So on this aspect, we have different tools and different solution expertise, as some of the things Vivek explained. So main tools which is in heart to the Digimat is Digimat MF, and MF means mean field homogenization. And with this one, we can the end user can able to create a Digimat card for their performance, the targeted performance. The performance can be anything. It's not just a static linear. It may be like impact or crash, or it may be like fatigue. Fatigue is a different performance which the companies do the simulations for a durability situations. Like that, for different target performances, you can create a Digimat card in Digimat MF, and they can able to couple the with softwares like Abacus, ANSYS, MSc Mark, MSc Nasdaq, these softwares by using the Digimat CA tool, where it will try to bridge the gap between the gap, and it will try to couple the Digimat models with the FE interfaces. So that is the objective. Today in this demonstration, maybe in the next 20 minutes, 30 minutes, I will give you the demonstration on the Digimat MF and how to create a card, and let us analyze deep into the card, and how the Digimat MF is predicting the anisotropy, which is a main challenge that industries are not able to predict the anisotropy. It is a very important point for the composite materials. So I just showing this flow tool. This is a Digimat. How when you're opening it looks like this. If you have a academic question software also, you can able to open like this. And there is a when if you are installing Digimat along with the documentation examples, there is a huge database of the examples which is available. When I'm clicking this one, you can able to go and see all the examples. You can go inside the Digimat MF and you can see the main what is the main aim or agenda of the Digimat MF, and after that, for every material composites can be in a different types. It is not just a single type in the world is using. Sometimes, let us say, for the OEMs and tier 1 companies, they are using for highly mass production parts, they use injection molded components. So let us say some companies which let us say supply chain was damaged and they want to use specific parts and they don't have it in the molds or dies. They go and straight away use additive manufacturing. They choose additive manufacturing and prepare a part in additive manufacturing. So like that, they prefer the different processes depends on their requirements and depends on their performances and depends on their targeted areas. So, for instance, these are some of the composites. One is the short fiber reinforced plastics, and is long fiber plastics, and SMC means sheet mold compounds. It is it is another version of the injection molding way of doing the processing. UD composites. UD composites means unidirectional composites. The fibers will be aligned, long fibers aligned in one direction in the resin. That's the UD composite. Like that, woven composites, foams, additive materials like SLS materials, FFF materials. So these are the two subparts of the additive manufacturing which Digimat will be supported. That is select line centering and fused filament fabrication or fused deposit molding. In metal and rubber also you can able to see the composite style of materials under the metals and rubbers. So it's not limited that your composite means something very only single type of process or single type of composite. It's like a different one. So now let us go into the agenda. What is MF will do? MF is actually analytical solver, and in the back, if you use a continuum mechanics equations and derived from the literature from by scientists, and it is very fast, efficient, accurate to compute the composite properties by when we are giving the inputs, individual matrix or resin properties, inclusion properties, and inclusion attributes, geometric attributes. When we are giving input of these things, these inputs can be easily given and they are available in online or in your database, individual properties. And when you are giving that and predicting the composite, it will predict the stiffness, strength, and even failure as well accurately, as you can see maybe in the experiments, etc. So at the same time, when you see the time which is taking to predict the composite behavior is actually a fraction of seconds. That is one of the advantage where the Digimat MF have, and that is very important for the industries. That time is very important to compute so that they will get the solutions quickly and analyze it quickly. So now I will go into the demonstration of this one, and I will add the inclusion properties, matrix properties, and inclusion geometric attributes, and I can run the analysis and show you the composite properties. So just before I'm giving, so even in this one, you may be able to see that the small tutorial in Digimat MF. This one will allow you to understand how to add the analysis. You can add the new analysis like this, and when you're right clicking and adding, you will get the three kind of graphic user interface like this. And after that, you can even click on the materials and right click on the materials to add the different phase of the materials. First phase of the material is matrix resin phase. And second phase of the material is inclusions. Either it is voids or inclusion is like carbon fibers or a chopped fibers or anything, something like you can say it is an inclusion. And like once you have added, and you can add microstructure. I will show that, and you can add the RVE. I will explain what is RVE and under the RVE section, failure, loadings, and finally we can see the composite performance under the result while performing step by step. So let us, I'll go into the Digimat MF. When I'm clicking this one, I can able to open this MF2. And just in the parallel, let me explain this one as well. This is another one is Digimat FE. The agenda of the Digimat FE is same as Digimat MF. That is to get the composite properties of the matrix of the composite. So when we are adding the individual properties, and it will give the composite properties. But in this here for the FE, Digimat FE means finite element homogenization, or we will say it's a full field homogenization, where actually we try to explicitly model the RVE. RVE means representative volume element, and we are trying to explicitly model the fibers, explicitly model the resin, and explicitly model the orientations. And we are actually doing the finally we are submitting analysis at the finite element software to run the analysis of the RVE and to get the composite performance. This is a little time-taking process, but it has some advantages over the Digimat MF, which the researchers are looking for and scientists are looking for, and some industry also in R&D centers they are looking for. So the agenda of the two Digimat MF and FE is same, but the approach is different. Where in this one they are actually going in the approach of solving the analytical solutions, but in this one they are going in the approach of doing the simulation on the RVE and getting the composite properties. So I will go briefly on the Digimat MF and show the one demo on this one. And with this one, I think if you have some doubts, we can I can try to clarify that with respect to the demo. So when I'm opening this one, it will be shown like this, and I can add the analysis here. So I have added the analysis now, and in Digimat you can able to do different analysis types, not only the just mechanical, but I can do thermomechanical, thermal, electrical. But at this moment, I will choose the mechanical one, and let us not disturb anything on this one about the homogenization settings. Where if you want to know more details about the homogenization scheme types, Mori-Tanaka double inclusion Taylor, there are all available in online documentation, which is even accessible to the any user, and not scheme. That is not disturb one, and this is integration parameter. This is also will not disturb, and we are giving these parameters to do the computation in the back in Digimat. Let me. It is already added one material. I will say that this material name is a matrix, or let us say first let us give the fiber material properties. I have the fibers inside the matrix, let us say, and I'm giving the fiber material properties, and my fiber material properties are elastic in nature and isotropic in nature. So I'm keeping the same thing. So elastic means we have to give the density and density modulus and Poisson's ratio. These are the basic properties of the elastic, which is anywhere you will get it for the glass fibers or carbon fibers which you are looking for. So let us say if I'm giving here 2.5 E minus 9 ton per mm cube. So I can give like this, and I can do the Young's modulus. Young's modulus is for this one 27,000 megapascal, and here it is 0.22 Poisson's ratio. So if you are giving at this moment, if you are giving this one, corresponding material stress strain plot can be visualized in the right side of the user interface. So when you're clicking click create, then it will be the bright one will be changed to the dark one will be changed to bright one. That means the section was assigned correctly. Let me go into the materials again and add another phase. Another phase means, let us say now I have added the fiber material, and now my fibers are filled in the matrix resin. So I'm trying to give the matrix properties now. So I'll give this one, and my usually the matrix is actually it will go beyond the elastic region, and it will go into yield. It will yield, and it will show some plastic region, and even it will fail after the some elastoplastic mm, scenario regions. So for the matrix, most of the times it is going to be the elastoplastic, and I'm giving the elastoplastic properties, and the popular plasticity model is J2 plasticity, and I'm using this hardening principle, exponential linear law, and I'm not changing these things. Let me validate this, and I will give now I will give the material properties corresponding to the matrix in the parameter session. So here I'm giving 1.1 density of the matrix is 1.1 minus 9. You can give the Higgs modulus, and Higgs modulus. Yeah, once you are giving Higgs modulus and Poisson's ratio, you can give. Uh, so yield stress, you can give yield stress is uh, these things. You may have a question that where you get these parameters. You will get these parameters specific to the matrix, maybe generic properties, not exact properties from the internet. You will take those generic properties, and first you will create a generic material card, and you will bring this one to high fidelity, or let us say improved material card. Uh, Once you have optimized these parameters, we will do optimization of these parameters at the Digimat MX. That is the purpose of the Digimat MX, that we do reverse engineering on this one by referencing in the material plots, and we are trying to fit a good fit with the experimental plots, and optimize the matrix properties. A matrix properties means this one under the matrix. So I'm giving some generic material parameters: hardening modulus 25, hardening exponent 25, Indian hardening 16. When I'm giving this one, and I can see the corresponding stress strain plot in the right side. So you can see that the first one is the elastic region, and here it is actually yielding, and it is going into the plastic region. It is, since we are given the hardening parameters, it is going to harden, and it will fail in some point of time. And this one we will specify in the failure section for this composite. So now I'm creating this one. Once I create, I can see that it is going to be created. So fibers and matrix are we are added to properties. So now let us go into the microstructure. Microstructure means here either fiber composite, fiber microstructure, or anything. Let me go into this one so that you will understand. So if I'm going into the microstructure, you can see that it can be added any kind of microstructure type, not as specific to just a fiber field. Even you can add the lattice kind of microstructure for additive manufacturing process types, and you can even add woven kind of microstructures, and you can add even sheet mold compound microstructure, etc. So now at this moment, I am going for the generic. Generic means either voids or fibers filled with the composite, that kind of microstructure. So in this one, I'm going into this one. So in the microstructure, I need to give the phase each time. So let us say if I'm saying matrix phase, I will go into the matrix. I will attach the specific matrix properties, and I will say that phase name, I will say it's resin. So I have added, and let me go into this and add one more phase. I will say this one is fiber orientations. I will say that fibers. Phase name is fiber. So the inclusion, either the phase type is either inclusion, voids, or continuous fibers. Now I will go and use the inclusions. You can even add the voids as well. The voids means sometimes manufacturing into the manufacturing, some materials they are having more voids, 20% voids, 10% voids, in order to get the accurate stress strain plots and material behavior corresponding to that voids. We have to embed the voids into the matrix so that we'll get that kind of properties. So now at this moment I will choose this inclusion, and I will go into the matrix. I will attach the material is a fiber, and I will validate this one. So the volume fraction, the volume fraction, I will say that my fibers content is 30% uh, volume fraction corresponding to the total volume. And here I will say that my aspect ratio here is nothing but L over D ratio. L means the length of the fiber, and D means width of the fiber. So I will say that my length is 20% higher than the width. Then the L over D will be like this. Sometimes when you are having the glass beads, circular beads, then you will give the one value. The one means it is actually circular one, and this one. For most of the times, the fibers will be around 20 to 30 aspect ratio. Then you can give the 20 aspect ratio. So let us have a little explanation on this orientation tensor. What is this? So what orientation tensor means how the fibers are aligned in the matrix. Um, if you see in this one, sorry, if you see in this one, maybe in this one, the fibers are aligned in this matrix in which direction? So is it in along the longitudinal direction, or in the transfer direction, or random directions, or some percentage probability 80% of the fibers are aligned in one direction, but 20% fibers are aligned in another direction, like that. So that will explain this will be described by just simply giving the orientation tensor in the under the orientation tab. So that's what actually the meaning of the diagonal elements. You don't need to touch upon the non-diagonal elements. You can keep them as a zero, but if you are saying that 100, that means all the fibers are aligned in one direction. But if you are saying that 0.3, 0.3, 0.33, I mean, that means actually I'm giving all the fibers are oriented in all the directions equally. So it is like showing the probability here. If I'm saying my fibers are oriented 80% in one direction, but 10% in another, but 10% in another, that means we can see that the only 80% fibers are aligned in one direction, but only 10% and another 10% you can see in the third direction. So this is how actually we give the tensor orientations, and you can create with this one. And once you have created it, you can go to the RVE representative volume element. So here we will add. Here the RVE means representative volume element through thickness. Either you can sometimes what is happening is for the injection molded components, when they are injecting the flag with the injection gate, the thickness actually fibers will be aligned in a different directions, let us say in a total number, like that. So when we can able to describe that using a multi-layer analysis, and we will add each layer, and for each layer we will describe the orientation tensor for the each layer. Like that we can add many number of layers, like 5 layers or 10 layers, we can add it like that to describe that orientation tensor through thickness. But at this moment, let us say that I want to use only single layer corresponding to the microstructure, which I have given under the microstructure tab. So let it be not the multi-layer at this moment. Do you have any questions as of now? Oh, I'm going to the failure. So here we can go and proceed further without failure as well. But if you are not getting the failure, what will happen is so it will what will happen. You can add failure also. I can add the one failure here, and so these things also. I am giving like this. I am activating this and let it be the default settings. But if you have any, if you want to know the clarification of the any options or something, please let me know. I'm happy to explain it after the session. So now I have defined the failure indicator. It is typically the Sahil 3D transfer isotropic. Most of the times we use it for the short fiber composites, but it's not limited to only this one. We have many number of failure criteria. You can use it specifically on material type. So I'm going into the loading and let me go and give the one loading topic. Here at this moment for the one analysis, I want to give the Excel loading and check it how it is actually behaving my composite behavior. So I'm saying that my peak strain is 0.03. So let it be like this, and let me create this one. So now the sessions were completed. All the blocks we have completed, and we can see all are in bright color. That means all are assigned correctly. Now I can run the analysis. So you can by clicking F5 or clicking this one, it will run the analysis. And you can see that the stress strain plot. So here we are seeing the stress strain plot, and for the one specific to the fiber orientation terms are this one, and loading is actually in x-axis along the fiber directions. Okay, let us say if I'm changing this one to 90, that means I am actually now loading the specimen for the RDE perpendicular to the fibers which are oriented most of the fibers, 80% fibers oriented in the one direction. That means uh, you can understand now the for the 90 degree the stiffness and strength are very less. So this is how actually we want to predict the material. It is an anisotropic in nature at every point in the part prepared by the companies. Now, if I even some locations, even it is having 45 degree or some other degree. Let us say if I'm giving 45 degree angle, validate. So what it will happen is it will show for 45 degree angle the sustain plot, and in not only the stiffness and strength, but the failure is also it will be different, and it will capture the failure also correctly with respect to the composites. So this is how actually we will create when we are saving this one. It will be saved in the .daf format, and you can use the DAF file in Digimat RT to create a coupled deck for the coupled analysis to run the simulations in your MSc Mark or NASDAQ or Abacus. So this is how actually we create the material cards. This is not only limited to the specific microstructure which I have proposed, but it is can be possible to create a different microstructures like a fabric, a lattice, a sheet mold compounds, or for metals. Uh, if you have actually the product with you, or even the student version with you, what you can do is you can able to explore those things using this examples manual, and for each module or for each tool, I think they have a different material cards. Let us say for SFRP or let us say UD composites, it has a card like this, and you can explore it by doing this one. The persons which the faculty which the people are doing research for research purpose also it is very useful. Particularly people are working on composites or composite materials or additive manufacturing for the polymers or polymer composites. They can use it mm, for advancing the research which they are doing. Uh, so this is the some basic tutorial which I want to explain to you at this moment. Uh, for your information, if you want to know more details about the Digimat product and case studies which companies are doing, I recommend to go into the EXtreme website and you can go to the resource section and you can watch the on-demand webinars and case studies available and brochure which explains all the tools and will tell you what is the objective of these tools and solutions. So same thing which I have done it can be done using the Digimat FE as well, but this one is explicitly modeling it in the Digimat FE2, creating a different microstructure, something like this, or even for microstructures which we can't able to model in Digimat MF can be modeled in a Digimat FE. Something like these things, these kind of things, multi-phase microstructures and multi-phase multi-layers. These kind of things possible to model in Digimat FE too. And the other tools like a Digimat map, the objective of the Digimat map is explained by Vivek that we are transferring the data from the one mesh to another mesh. This is very important tool for the industries where industries having different meshes, but they want to transfer from one mesh to another mesh. That can be possible to do with the Digimat map tool. And uh, if to know more details about this one, again, I refer to go visit the website and more details about that and even case studies are available, webinars are available with respect to this one. And L2 manufacturing is the process simulation tool where we try to print the virtually the simulation in Digimat AM to get the residual stresses, Warpage and um, etc. For the print before you are printing the part to understand it whether it is you are getting a real part or what we want, etc. So so with this one I'm ending my demo here, but you can don't hesitate to contact me if you have questions or you can even send me if you want you can send me mail to clarify the doubts or questions. Thank you. we will give the feedback link. I think Vivek sir will provide the feedback link maybe shortly after the call or something, sometime, so that he will try to fill the feedback in online itself to submit it. Thank you everyone. Vivek, are you there?
Hello, sir. Can you hear me, sir?
Yes, I can hear you.
Sir, shall we wind up the session, sir?
Yes.
Okay, sir. Now I request Mr. Rajiv Gandhi to deliver that vote of thanks.
On behalf of Sanskrithi School of Engineering, I extend a heartfelt thanks to our chief guest, Mr. Vivek, Business Development Manager, Hexagon MSc Software Bangalore, Indo-Pacific region, and also special thanks to our co-host, Dr. Harish, Hexagon MSc Software Bangalore, who took time from his enlightened our mind and shown a new path. And also, I extend thanks to staff members for their enormous cooperation within the session. I, I would like to thank to HODs of civil and mechanical and faculty coordinators who worked behind the scene to make this event happen. Thank you, sir. From any questions from audience side? Is there any questions? Everyone fill your feedback link as soon as possible.
Thank you all. Have a nice day.